Hello, everyone, and welcome to another AP Chemistry virtual lesson. My name is Michael Faribault, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. Today, the topic of today's lesson falls under Unit 9. Now, we've talked about this before, you may remember this, but if not, I'll go ahead and give you the disclaimer that on the AP exam this year in 2020, it covers Units 1 through 7. But the College Board and colleges have decided that there are certain topics in Unit 8 and Unit 9 that are still worthy of study and focus, especially as you prepare for your next course in chemistry in college. So I will focus today on topics that are very important in chemistry, but will not be covered on this year's AP Chemistry exam. A reminder to students to go to apstudents.org/exams2020 to get more information about the format of the AP exam. For chemistry, the AP exam date is May 14th. And there's information here on the screen about the different time zones in which you'll be taking the AP exam, depending on where you live in the world. And there are 2 free response questions on the online AP Chemistry exam this year. So let's get into our lesson for today. Hopefully you have access to a periodic table, scratch paper, something to write with. We'll talk about in Unit 9, entropy, Gibbs free energy, thermodynamic favorability, and the connection between free energy and equilibrium and dissolution. And you can see not only the topics here, but also the skills and science practices. So in our overview today, we'll talk about entropy, free energy, and thermodynamic favorability, and as free energy relates to equilibrium and dissolution. Our warm-up problem for today's lesson is the AP Chemistry practice exam question that I had given you in yesterday's lesson for homework. And so this question relates to solubility equilibria. So we have a saturated solution of magnesium fluoride, MgF2, and that was prepared by adding 0.50 grams of solid magnesium fluoride to 100 milliliters of distilled water. Now, again, it's a saturated solution, so we have to assume that not all of the solid dissolves, and at the end, this saturated solution most likely has some solid magnesium fluoride that is on the bottom of the beaker. Now, when this saturated solution is analyzed, it is determined that the concentration of the fluoride ion in this saturated solution is 2.4 times 10 to the minus 3 moles per liter. All right, so Roman numeral 1 of this question, write the chemical equation for the dissolving of solid magnesium fluoride in water. So we have our solid magnesium fluoride, and it dissociates into magnesium ions and fluoride ions. So make sure that you balance your equation and that you include the charges on the ions. You don't necessarily have to include the phases of matter, in this case, S for solid and AQ for aqueous, but I just did that just to be complete. Definitely make sure you have the correct symbols, charges, and that the equation is balanced. The next part of this question asks us to calculate the number of moles of magnesium fluoride that dissolves. So we are not going to take the 0.50 grams of solid magnesium fluoride and convert that to moles. We have to assume that not all of that solid actually dissolves. Now we are given a number, and that number is the molarity, so the concentration in terms of moles per liter of the fluoride ion. But remember that there is a 1-to-2 mole ratio between the number of moles of the magnesium fluoride and the number of moles of the fluoride ion. So we have to make sure to include that 1-to-2 ratio in our conversion factor. Otherwise, if we calculate the number of moles of the fluoride ion, that will not be the number of moles of the magnesium fluoride. It would be twice as much, so we'll have to cut that number in half. So we'll start with the 100 milliliters, which is the volume of the saturated solution. We're going to use molarity as a conversion factor. So I could write 2.4 times 10 to the minus 3 moles of fluoride over 1 liter. I have chosen to write 1,000 milliliters instead of 1 liter, but that's because I wanted to get the milliliters to cancel out. Now, the second step is to convert moles of fluoride into moles of magnesium fluoride. There's that 1:2 ratio I mentioned. And so if we do this math, we get 1.2 times 10 to the negative 4 moles of magnesium fluoride. So that is considerably less than the amount of moles of magnesium fluoride that was added. That's how much actually dissolved. Now for the next part of this question, they want us to calculate the value of the KSP. So the KSP would be the concentration of the magnesium times the concentration of the fluoride squared. So remember that the concentration of magnesium is not 2.4 times 10 to the minus 3, but rather half as much. If we plug in these numbers into our KSP expression, that's 1.2 times 10 to the minus 3 times 2.4 times 10 to the minus 3 squared, then we get our value for the KSP, the solubility product constant for magnesium fluoride, 6.9 times 10 to the minus 9. All right, so we have a part B of this question. And now we're done with magnesium fluoride, and we're going to talk about some other fluoride salts from the alkaline earth metal family. We have calcium and barium. So a beaker contains 500 milliliters of a solution in which both calcium ions and barium ions are present in a concentration of 0.1 moles per liter. The student intends to separate the ions by adding 0.20 molar sodium fluoride, 1 drop at a time, from a burette. And they're giving us the KSP value for calcium fluoride and for barium fluoride. You can see that they are different. So calcium fluoride's KSP is about 5 orders of magnitude smaller than barium fluorides. And that we can take advantage of that difference in KSP because it helps us understand that there's going to be a difference in solubility. Which salt will precipitate first essentially is asking the question, which salt is less soluble in water? And hopefully you remember from yesterday's lesson, the smaller the KSP, the lower the solubility. So the value for KSP for calcium fluoride is smaller than that of barium fluoride. So therefore, calcium fluoride has a lower solubility, and calcium fluoride is the salt that should precipitate first. Well, that was just qualitative. Now we'll actually do a quantitative calculation. Calculate the minimum concentration of fluoride necessary to initiate the precipitation of the salt. So we have 0.1 molar concentration of calcium and barium. And this is our KSP expression for calcium fluoride. Let's plug in 0.1 molar for the concentration of the calcium and then solve for the concentration of fluoride. This will tell us the minimum concentration of fluoride necessary to initiate precipitation of the calcium fluoride. So we'll go ahead and multiply both sides by 10, essentially dividing by 0.1. So now we have F squared, the concentration of fluoride squared is 3.5 times 10 to the minus 10. And then we have to square root this answer, or square root the number to get our answer. So the concentration of fluoride is 1.9 times 10 to the minus 5 moles per liter. That is the concentration of fluoride needed for the first grains of solid crystal calcium fluoride to appear. So now that we know that number, calculate the minimum volume of the 0.2 molar sodium fluoride that must be added. And again, we're assuming that the amount of sodium fluoride is so small, it doesn't change the total volume. So we still have essentially a 500 milliliter volume of solution. And then the concentration, 1.9 times 10 to the minus 5 moles of fluoride per 1 liter or 1,000 mils. So this number, 9.5 times 10 to the minus 6 moles of fluoride, that needs to come from a solution that has a concentration of 0.2 moles per liter. We're going to use the sodium fluoride molarity as a conversion factor, but this time putting moles on the bottom. and volume on the top. So how much sodium fluoride do we need? A very small amount. In fact, less than 1 milliliter. So what I did was I multiplied volume times molarity to get moles, and the molarity was from Roman numeral 2 in this problem. Then I did moles divided by molarity, essentially to get volume. So in the official scoring guidelines, you'll see a slightly different approach to what I did, and they still get the same answer. So they did M times V equals M times V, since the moles are not changing. So 0.2 molar, which is the sodium fluoride, times some volume we don't know yet, equals the 1.9 times 10 to the minus 5 molarity, which is the concentration of the fluoride needed, and then times the volume of the solution, the 0.5 liters or 500 milliliters. So as you can see, they got 0.047 or 0.048 milliliters. All right, there was a part C of this homework question, and it says, there are several ways to dissolve salts that have limited solubility. Describe one procedure to redissolve the precipitate. So one way to redissolve a slightly soluble salt is to add more water. Another way would be to heat it up, increase the temperature. Any valid statement that implies a shifting of the equilibrium toward the products. So they also mentioned adding acid. So the fact that calcium fluoride dissociates into calcium ions and fluoride ions. I talked about this in yesterday's lesson. It turns out that since fluoride is a weak base, adding H+, it will react with the fluoride, causing this concentration of fluoride to go down as it forms the molecular version of HF, the hydrofluoric acid. So as it decreases that concentration of fluoride, then that will shift the equilibrium toward the right. So again, either adding more water, adding acid, or heating the solution would increase the solubility. All right, so for today's lesson, I'm going to start with entropy. Now, entropy is famous, or maybe I should say infamous, for being poorly understood by students. It's a difficult concept to teach. Many teachers try to use analogies, and the analogies sometimes create misconceptions. So one of the most common analogies for entropy is disorder. Disorder, randomness, chaos, a messy room, a shuffled deck of cards that's dropped on the floor so that the cards are scattered. So the problem with saying entropy is disorder is it's actually more complicated than that. I'm not going to go into the great details today of things like microstates, but I'm going to go ahead and define entropy in a way that will help you earn credit when you answer a question on an exam. Now, it may not be on this year's AP chemistry exam in 2020, but for any chemistry test in which you have to justify your answer, I'm going with the statements and phrases about entropy that I find in textbooks as well as the course and exam description for AP chemistry. So you'll see on the screen definitions of entropy that I think are helpful. So entropy is a measure of how dispersed or spread out the energy of a system is at a specific temperature. Entropy increases when matter and or energy becomes more dispersed or spread out, and we're focusing on the particles of matter or the energy itself. Entropy increases when a substance changes phase from a solid to a liquid, from a liquid to a gas, or from a solid to a gas. Again, all of those phase changes would increase entropy as the particles become more dispersed and spread out. And entropy increases when individual particles become freer to move and generally occupy a larger volume. So for example, if you let air out of a tire, then the gas molecules spread out to a random, more wide spread out region. Entropy increases when a gas expands into a larger volume at a constant temperature. Entropy in a chemical reaction increases when the total number of moles of gaseous products is greater than the total number of moles of gaseous reactants. So if you go from 2 moles to 3 moles of gas, that would increase the entropy. And you may remember seeing Boltzmann distribution curves. So I'll just try to sketch one here real quick. So we typically are talking about something like kinetic energy, or sometimes molecular speed. So I'll just put number of molecules here. And then this could be either energy or speed. So speed, or sometimes kinetic energy, I'll just say KE for short. So you'll notice that when you switch to a higher temperature, this would be a higher temperature, that the area under the curve stays the same, but there is a broader distribution of the energies. So again, entropy can be thought of as a dispersal of the energy. So when the temperature increases, the entropy of the system increases. Now, where on your equation sheet do you find entropy? Well, again, this is our formula for calculating delta S. If you know the entropy of the products and the reactants, you may recall that we've already done work with this equation in Unit 6, talking about thermodynamics and thermochemistry. So the delta H of formation, the enthalpy of formation of the products minus that of the reactants. What's also interesting to note is that while the delta H of formation for an element in its standard state, a pure element in its standard state by definition is 0. Here, these values for elements are not 0. So the delta H has to do with enthalpy and the heat involved, the energy involved in the formation of 1 mole of a substance. Well, you're not going to form 1 mole of an element from an element. So these already are elements. So by definition, they would be 0. But since we're not talking about enthalpy, but rather entropy, the only thing that would have an entropy value of 0 would be a pure crystal that is at absolute 0. So you'll find that if you look up in a table, the entropy values, they will always be a non-zero number. There's a slightly different situation for aqueous ions. Aqueous ions are defined relative to H+, and so you will see a 0 for that. But for a pure substance, solid, liquid, or gas, as opposed to aqueous ions, you will never find a 0 in these tables. All right, so I have an equation, and this equation involves 1 mole of nitrogen reacting with 3 moles of hydrogen to produce 2 moles of ammonia, NH3, and these are all gases. So think about what I mentioned earlier about the entropy change for a chemical reaction and make a prediction. Should the delta S, the change in entropy for this particular reaction, which goes from 4 moles of gas to 2 moles of gas, should that be positive or negative? So here's a hint. If entropy is increasing, the delta S is positive. If delta S is negative, it means the entropy is decreasing. So think about what happens when you go from 4 moles of gas to 2 moles of gas in terms of the change in entropy. All right, let's go ahead and do the calculation. So we'll do products minus reactants. That would be 2 times the number for NH3 minus the number for nitrogen, and then also minus 3 times the number for hydrogen. And then this math works out to be negative 198.3. So hopefully that agrees with what you had predicted, that when you go from 4 moles of gas to 2 moles of gas, the entropy decreases. And so that's why the delta S is negative. Let's take a look at a few more examples of this concept. Here we have the conversion of ozone, which is O3, to molecular oxygen, O2. Think about whether you should increase or decrease entropy. We're going from 2 moles of gas to 3 moles of gas. So 3 times the number for molecular oxygen. that's the products, minus 2 times the number for ozone. So now we get a positive value, but this should make sense to you. It's a contrast to the last example. Now the number of moles of gas is increasing from 2 to 3, so the entropy increases and we have a positive delta S. All right, here is a phase change from liquid water to steam or water vapor. So think about whether entropy should increase or decrease for this change. Going from a liquid to a gas, think about what the particles are doing, whether they are more spread out or closer together or farther apart. So we'll go ahead and take the 188, which is the number for water vapor, minus 69.9, the number for liquid water, and we get a positive delta S. So as you go from a liquid to a gas, that is a phase change in which entropy is increasing. Here we have 2 moles of solid sodium reacting with 1 mole of gaseous chlorine to produce 2 moles of solid sodium chloride. So think about whether that entropy should increase or decrease and whether the sign of delta S should be positive or negative. So we'll take 2 times the number for NaCl minus 2 times the number for sodium plus the number for chlorine. So we're starting with 2 moles of solid and 1 mole of gas, and we're ending with 2 moles of solid. So hopefully your prediction came true and that the delta S is negative. This tells us that entropy is decreasing as we are converting from essentially a gas and a solid to just a solid. So there are less degrees of freedom and there are fewer arrangements of the molecules and the particles as you go from a gas to a solid. Okay, so I've talked about entropy. I would like to also talk about free energy and thermodynamic favorability. Some textbooks, and depending on your teacher, maybe the teacher might use this phrase, will use the term spontaneous. But the AP course and exam description tends to avoid the word spontaneous, and they instead prefer the phrase thermodynamically favorable. So what exactly is free energy? Well, the amount of energy that is free or available to do useful work. And so if I say a reaction is favorable or thermodynamically favorable, that typically means that it happens all by itself and that can be used to do work on the surroundings. Otherwise, if the reaction is not favorable, then the surroundings would essentially need to supply energy to the system to make that reaction happen. So the delta G is our symbol for the Gibbs free energy change. And we're talking about the little superscript 0 means standard conditions. That's typically 1 molar for aqueous species, 1 atmosphere or 1 bar for the pressure of gases, and standard temperature 298 Kelvin for thermodynamic standard conditions. Now earlier we said that if delta S was positive, that meant it was increasing entropy. And if delta S was negative, then entropy was decreasing. So with free energy, it goes like this. If the change in free energy is negative, then the process is favored to occur at standard conditions. So you actually would have a positive delta G indicating it's not favored. A negative delta G indicates that it is favored. Now, this is not kinetics. This is thermodynamics. So whether it's favored or not says nothing about the rate of the reaction. It could be fast or it could be slow, but if the delta G is negative, this is where I talked about that word spontaneous before. We tend to avoid the word spontaneous because some people have the connotation that spontaneous means fast. And so we're not talking about the rate. So thermodynamically favored just means it's going to happen, whether that takes, 5 seconds or a year. One way to calculate the value of delta G is very similar to the equation I showed you earlier, products minus reactants, where you have a table and you'd be given the standard free energy change for individual chemicals, the free energy of formation. Another way to calculate delta G, and these equations are on your equation sheet, is the Gibbs free energy equation involving all 3 of these concepts: free energy, enthalpy, delta H, and entropy, delta S. These are all combined, and the T stands for the absolute temperature in Kelvin. All right, so free energy and thermodynamic favorability. Well, there are essentially three possibilities for delta G. It could be negative, positive, or zero. If delta G is negative, as I said, it means it's favored. The forward process, as in the reaction as it's written from left to right, is favored to occur. But if delta G is positive, then the forward process is not favored to occur. Instead, the reverse process would be favored. Or you could say that energy must be supplied from the surroundings in order to get the forward process to occur. Now, if delta G is neither positive or negative, this often happens for a phase change where, for example, you're melting ice and you're exactly at 0 degrees Celsius or 273 Kelvin. So neither the forward or the reverse process is favored if you have this perfect equilibrium situation where essentially both the forward and the reverse processes are happening at the exact same rate. Otherwise, if K, the equilibrium constant, is large, you're favoring the products. And if K, the equilibrium constant, is very, very small, you're favoring the reactants. And we'll talk about the relationship between free energy and the equilibrium constant a little bit later in this lesson. All right, so here's some examples of products minus reactants. Notice that the delta G of formation for a pure element is 0, as it was for enthalpy, the enthalpy change of formation. So I have the synthesis of liquid water from the elements hydrogen and oxygen. Products minus reactants gives me a value of negative 474.4 kilojoules per mole of reaction. So what does this negative delta G tell me about the thermodynamic favorability of this synthesis of water? Well, you may have heard of the Hindenburg airship that burst into flames. And again, hydrogen was inside the ship. You may have done experiments in your chemistry class involving a little popping sound as a test for hydrogen gas. Hydrogen, the combustion of hydrogen, although it does need a spark or an ignition source to get it started, it is thermodynamically favorable. So once you can get the reactants over the activation energy barrier, which is what that spark is doing, then the reaction starts and it proceeds on its own. And one of the examples of free energy, how it can do useful work on the surroundings, is the launching of something like the space shuttle. So that's powered by hydrogen and oxygen. So obviously doing very useful work in that situation. What if I take the synthesis of water and write it backwards? If the forward process is favorable, then what do you think about the reverse process? Well, hopefully you understand if I take negative 474.4 and just flip it around, I now have a positive. So this is not the synthesis of water, but rather the decomposition of water. So the electrolysis of water can occur, but it's not thermodynamically favored. It doesn't happen all by itself. So energy in the form of a battery or some power supply must be provided from the surroundings to the system for that reaction to occur. Here's another example of a decomposition equation, a reaction. This is hydrogen peroxide, H2O2. I'm going to go ahead and think about hydrogen peroxide in terms of what you might find in your medicine cabinet somewhere at home. I'll do the math of products minus reactants, and I come up with a negative value. Now, the decomposition of hydrogen peroxide is favored, however, without an enzyme. So when you pour hydrogen peroxide on a scrape or cut and it fizzes and foams and sometimes stings, the enzymes in your skin called catalase are making that reaction go faster. You can also add various chemicals like potassium iodide or manganese dioxide to catalyze the reaction. Just because it's favored doesn't mean it's fast or slow. So remember that in general, thermodynamics will only tell you if it's favored or not, but it says nothing about the speed with which the reaction occurs. In general, if the activation energy tends to be relatively high, then the reaction will usually occur rather slowly. So if you are asked a question, explain why, although a reaction is favorable, it doesn't seem to occur at a very observable rate, you could talk about the activation energy being high, and that's why the rate of the reaction is slow. All right, here's another reaction. This is the decomposition of calcium carbonate. which is found in limestone, and it decomposes to give calcium oxide and carbon dioxide. So we now have data for delta H, and that's the enthalpy of formation, and we have S, so the entropy. We'll do products minus reactants for each of these sets of tables. So I have products minus reactants, and I get a delta H of positive 178.5. This indicates that the decomposition reaction is an endothermic process. We're going from 1 mole of solid to 1 mole of solid and 1 mole of gas. Now, gas has typically more entropy than a solid because the particles are freer to move around. There's more arrangements of gaseous molecules than solid particles. So I would predict that the delta S is positive, and that's what happens when I do this math. So I did products minus reactants using the numbers in the table on the left. Entropy increases as 1 mole of solid is converted into 1 mole of solid and 1 mole of gas. The particles are freer to expand into a larger volume. Let's put these two things together. We have a delta H, which is positive 178.5 kilojoules per mole, and we have a delta S, which is positive 159.0 joules per mole Kelvin. Now notice what I did because I was worried about units. So I converted by dividing by 1,000. I went from joules to kilojoules because I wanted the units of delta H to be the same as the units of delta S. So watch out for that. If you're solving problems, pay attention to your units. All right, so delta G would be delta H minus T delta S. Is the decomposition of calcium carbonate thermodynamically favored to occur at 298 Kelvin or 25 Celsius? So there's our equation. We'll plug in our numbers. And again, notice I have changed my delta S into units of kilojoules, so it will match. The kilojoules are going to be present in my final answer. The Kelvin will cancel out. And so I did this math and I got a positive value. So the answer to this question is no. The decomposition of calcium carbonate is not thermodynamically favored to occur at 25 degrees Celsius. Well, what if I choose a different temperature? It is an endothermic reaction, so maybe I have to heat it up. I'm just going to go ahead and make up a new temperature, and we'll do this calculation again. So is this decomposition favored to occur at 1,000 degrees Celsius, which would be 1273 Kelvin? So I'm going to go ahead and assume that the delta H and delta S values are going to remain the same. That's my assumption. All I'm doing is plugging in a new number for the temperature. And now when I do this math, the delta G is negative. So it is favored to occur at 1,000 degrees Celsius, but it was not favored to occur at 25 degrees Celsius. So my next question is kind of related to these two results. Determine the minimum temperature that would be required in order for this reaction to become favored. So how do I switch from not favored to favored? Well, I have to heat it up, but at what point? What's the minimum temperature that would be? If delta G is equal to 0, then neither the forward or reverse process is favored. This would be the point at which it switches. So I'm going to go ahead and solve the equation. I set the delta G equal to 0, which means that delta H equals T delta S. Divide both sides of the equation by delta S. Again, watch out for units. So we have kilojoules on both the top and the bottom. Now I'm going to get my answer in units of Kelvin. So around 850 Celsius would be the temperature that would be required at least to make this reaction occur. Okay, so I want to talk a little bit more about the connection between free energy and temperature. Now, focusing on our delta H and our delta S, there are 4 possibilities. We have in the first row of this table here what I'm going to call this a best case scenario. And then the next row of the table, I'm going to call this a worst case scenario. And then in these examples, I would say in general, it depends. Well, it depends on what? It depends on the value of the temperature. So in terms of the T and the delta H minus T delta S, then that temperature is going to be important in certain situations. Okay, so best case scenario, if delta H is negative and delta S is positive, then delta G will be negative no matter what. So favored at all temperatures. Unfortunately, if we go the other way, delta H is positive and delta S is negative. Hopefully you can see by plugging those values into the free energy equation there at the top left, that's going to make delta G positive no matter what. So not favored at any temperature. Now, if they're both positive, delta H and delta S are both positive, then you would want this portion of the equation should get your focus. So if delta H is positive, that's not going to help our situation. We're trying to get delta G negative. So that would only be favored whenever the value of T is relatively high. And if instead delta H is negative, so that's a good thing. But now the delta S is positive. If T is rather large, I'm sorry, if delta S is negative, if T is rather large, you have a negative times a negative. So that's actually going to make this term positive and is going to lead to a potentially positive delta G overall. You want the T to be low. So I'm going to go ahead and explain a little bit more about these last two scenarios. When I say favored at high temperatures or low temperatures, what does that mean? So these are my it depends situations. Okay, so I want delta G to be negative. That means it's favored. This is not helping me. However, this is a good thing and therefore could potentially make the overall value of delta G negative as long as this T is large enough. So you want a high value for temperature because then this portion will be negative and make the overall delta G negative. You can also think of this in terms of Le Chatelier's principle. So we have a positive delta H, which means we have an endothermic reaction. You may recall from an earlier lesson that as temperature is increased, the endothermic reaction will shift in the direction of the products. That would make the reaction more favorable. So an endothermic reaction tends to be favored at high temperature. Now, if we do the same kind of scenario here, we have delta G is negative. We want this to be negative. So therefore, this part, which is the delta H, that's a good thing. But unfortunately, a negative times a negative is a positive. So we do not want this term to overwhelm the delta H. So therefore, only at low temperatures would this reaction be favorable, because if T gets too high, then the T delta S term might have a greater magnitude than the delta H, so low temperatures. And going back to the Le Chatelier's principle situation, if you raise the temperature too high, then what that can do by shifting the equilibrium toward the reactants, it can decrease and potentially make your reaction unfavorable at relatively high temperatures. All right, well, hopefully that helps you understand a little bit more about the temperature dependence of delta G. You might sometimes see a question that asks you about what drives a particular chemical reaction, like what's the driving force? And there are three possible answers. The reaction is driven by enthalpy only, which is delta H. It is driven by entropy only, so delta S, or it's driven by both. Well, if you have a negative delta H and a negative delta S, again, the example being that we're trying to get delta G negative, so this would be a good thing, and this would not be a good thing. So focusing on the enthalpy only, if delta H is negative and delta S is negative. Now, driven by entropy only, if you have a positive delta H, this cannot be the driving force because, again, you're trying to get delta G negative. This positive delta S is helpful because, again, that makes this T delta S term overall with that negative sign there, that can potentially be the driving force. So it can be driven by either a negative delta H, or it could be driven by a positive delta S, or if you have both, That's your best case scenario, then it's driven by both. All right, let's talk about free energy as it relates to equilibrium. You should know that K is either more than 1 or less than 1, indicates something about products being favored or reactants being favored. So if the delta G is negative, then we are favoring the products and K is greater than 1. If delta G is positive, we are favoring the reactants and K is less than 1. And there is an equation on your equation sheet that looks like this. So if you look at the natural log portion of this equation, the natural log of a number that is less than 1 will be negative. So a negative times a negative is going to give you a positive delta G. But the natural log of a number that is greater than 1 will be positive. And so you'll end up with a negative delta G. Now, as far as the R, that's the ideal gas constant, we're going to be using this particular value of R because it has joules attached to it. So pay attention to your units. When you have to use a particular value of R that involves delta G in this equation, you want to use 8.314, and that has units of joules per mole Kelvin. All right, I want to talk about free energy of dissolution, then we're going to do some AP chemistry practice. Dissolution means dissolving in water. So I have a chemical called ammonium nitrate, NH4NO3, and I've got some delta H of formation data and entropy data on the left. So the dissolution of ammonium nitrate. What about the delta H or the enthalpy? If we plug in the numbers from the table, we get a positive value. Now you may know this. If not, it's a little fun fact to know. There are some things called instant cold packs. I might have mentioned them in an earlier lesson. Instant cold packs typically contain a substance like ammonium nitrate. And when dissolved in water, there's a little pouch of water on the inside of the bag. So you kind of twist the bag until that little pouch of water breaks. As it dissolves, everything gets cold. So an endothermic dissolution means that the surroundings are actually donating heat to the system and the surroundings get colder as a result. So there is our positive delta H. We're going from 1 mole of solid to 2 moles of aqueous ions. If I calculate delta S from the data in the table on the left, I get a positive delta S indicating that entropy is increasing. So we might say that the particles are freer to move around as they have broken off the crystal lattice and now can move more freely throughout the aqueous solution. So a positive delta H and a positive delta S. I'm testing you here. What's our value of delta G? I'll give you a hint. This is a soluble ionic compound. It's very soluble. So what would you predict your delta G to be, positive or negative, if this reaction is going to occur? Well, I'm going to go ahead and plug in the numbers. Again, watch what I did there as I divided the delta S by 1,000, so I could get my units in kilojoules, so pay attention to that. And the delta G is in fact negative 4.3 kilojoules per mole, so the dissolution of ammonium nitrate is favored to occur. Is this process driven by enthalpy only, entropy only, or both? So consider the sign of delta H and delta S. Which one or both is driving the dissolution of ammonium nitrate? Well, as I mentioned earlier, when you have a positive delta H and a positive delta S, again, the positive delta H indicates it's endothermic. That can never be a driving force. But a positive delta S absolutely is a driving force. So this is driven by entropy only. So in terms of the dissolution process, you can think of the dissolution of an ionic solid in 3 steps. Now, these steps all happen simultaneously, but let's break it down into 3 separate events. You have the solute, which is the crystal. So that's going to be breaking the attractions, and that would be an endothermic process. So delta H is positive. It's also going to create more freedom of movement, so more arrangements. So delta S is positive. Entropy and the free movement is increasing there. So entropy is increasing. You have to break up some solvent interactions. That will also lead to a positive delta H. Again, anytime you break an attraction or a bond, you're breaking attractive forces that requires the input of energy, so endothermic. And again, we're pulling the particles apart from each other. So again, a positive delta S. Now, whenever the solute and the solvent form these ion dipole forces, there's actually slightly less degrees of freedom for the ions that are now hydrated. So that's actually going to result in a negative delta S. So a reduced degrees of freedom there for those particles that are bound to those water molecules. And again, when you form an attractive force, that is going to release energy. So breaking a bond absorbs energy, forming a bond releases energy. So negative delta H and negative delta S because of a slight decrease in entropy. All right, so I've got some AP practice problems to do, and then that will wrap us up here. Okay, so here are some practice problems that relate to entropy, enthalpy, and free energy. We have an equation. A student designs an experiment to study this reaction. And in thermodynamic terms, a reaction can be driven by enthalpy, entropy, or both, considering that the flask gets cooler as the reaction proceeds. What drives the chemical reaction here? So if it gets colder, like the ammonium nitrate dissolving in water, when it gets colder all by itself, that is an endothermic process. That would be a positive delta H. That is not going to be the driving force. But we know that it does occur. It definitely happens. There's formation of bubbles. So this reaction does occur, but it's driven by entropy only. So reactions are thermodynamically favorable when delta G is negative. Since the reaction is endothermic, the flask gets cooler, delta H is positive. The reaction is not driven by enthalpy because enthalpy does not help make delta G negative. Because there are no gases in the reactants and one of the products is a gas, delta S must be positive, which helps to make delta G negative. So driven by entropy and the formation of the gas, increasing entropy. All right, here is a new question. You might have a little deja vu on this question. We did talk about this in an earlier lesson in Unit 6. This is calculating the delta H by doing bonds broken minus bonds formed. So you may have to watch that earlier lesson because I'm going to go ahead and just cut to the solution there that I had already shown you in an earlier video. So it's a conversion from fulminic acid to isocyanic acid. That's 1 mole of gas going to 1 mole of gas. And we have now calculated from the bond enthalpies that the reaction is exothermic, so negative delta H. A student claims that the reaction has a delta S close to 0. Explain why the student's claim is accurate. So we're not changing phase here, and we're not changing number of moles. So the change from fulminic acid to isocyanic acid is in a rearrangement of the atoms, but there's no change in phase and no change in the number of molecules, so delta S should be pretty close to 0. Which species the reactant or the product is present in higher concentration? This is our connection between delta G and the equilibrium constant. Well, we know that delta G equals delta H minus T delta S. We've already established that delta H is negative and delta S is pretty close to 0. So therefore, delta G is essentially equal to delta H. So we have roughly negative 246 kilojoules per mole for our delta G. That means that the reaction is favorable. Since delta G is negative, that means that K, the equilibrium constant, is greater than 1. There should be more products than reactants. So the product, isocyanic acid, will be present in higher concentration. We made the connection from delta G to the equilibrium constant being greater than 1. All right, here is a new practice problem. We have an equation between NO and NO2, so nitrogen monoxide reacting with nitrogen dioxide to produce N2O3. We have to calculate the value of the equilibrium constant, and we are given the delta G in the table. So we're going to calculate the value of the equilibrium constant by rearranging this equation, which is given to you on the equation sheet. I'm going to divide both sides by the negative RT, and then I have to do the opposite of a natural log, which is the e raised to that power. Now be careful that you have to focus on your units, because this delta G is in kilojoules, but the R, the ideal gas constant that we're pulling off the equation sheet, is in joules. So watch out, you don't put in 0.87 on the top there, but rather 870, because that would have units of joules. Alternatively, you could have divided 8.314 by 1,000. So either one, just pay attention to your units. I did this math, and I got that my K happens to be a little bit less than 1, so it's 0.7. Next part of this question says, if the pressure of the nitrogen monoxide is 1 atmosphere, and the pressure of the nitrogen dioxide is also 1 atmosphere, will the pressure of the N2O3 be 1 atmosphere at equilibrium? Look at that value of K. Is that relatively large or small? Well, K is less than 1. That means that this reaction does not go to completion. The only way the pressure of the N2O3 would be 1 atmosphere at equilibrium is if the reaction went to completion. Since K is less than 1, this indicates that there will still be a certain amount of reactants present at equilibrium, so we disagree with that particular question there. A student hypothesizes that increasing the temperature will increase the amount of N2O3. Okay, so if you raise the temperature, are we going to shift this equilibrium toward the formation of N2O3? Well, that would be true if we have an endothermic reaction, but we don't. We have an exothermic reaction, so I disagree with this hypothesis. This reaction will be exothermic because delta H is negative, so therefore with an exothermic reaction, increasing the temperature will actually shift the reaction toward the left, the reactants. This would cause the amount of N2O3 to go down, not up. All right, so some more practice problems. Here we have the dissolution of a chemical. This is called urea, and it's featured right up here. And it says, calculate the concentration of the urea. So we're given information about grams. We can definitely convert from grams to moles, and then moles divided by volume in liters. So that problem gives us 17.9 moles per liter. The student also determines that the concentration of urea at 25 degrees Celsius, not 20, but 25 degrees Celsius, is 19.8. So what just happened is we raise the temperature and we increase the concentration. That results in a shift toward the products. That indicates that the reaction must be endothermic, because when we raise the temperature, we increase the concentration of the product. That's Le Chatelier's principle. This is about a procedure for making the reaction. Well, actually not really a reaction, but a dissolution. And it says, list the specific measurements that are required. So you don't actually have to write a procedure, I'm sorry. You have to actually write the measurements. And the measurements would include, let's measure the mass of the urea, the mass of the water, initial and final temperature. There were students on the AP exam that got this question correct, but they wrote an entire procedure. Didn't have to do all of that, just simply list the measurements. Delta T, by the way, is not a measurement. So initial temperature, final temperature, those are measurements. All right, so we have an entropy. Delta S is 70.1. That's products minus reactants. So we have 70.1 equals the product, which we don't know right now. That's the question mark in the table, minus the reactant 104.6. And we just solve and we get 174.7. I'm going to tell you right now that looking at the clock, I know I want to wrap this up pretty quick, so I want to thank you for hanging in there with me. The good news is there's not going to be any homework in today's lessons. I'm going to explain that in just a second, but feel free to pause the video because I am going kind of fast through these last few slides to finish up our discussion of free energy, entropy, and thermodynamics. They're asking for a particle level explanation for why the delta S is positive. It has to do with the fact that the particles are more free to expand and move around. Definitely want to talk about the particles in this case being more free to expand and move around or have a greater number of possible arrangements. So delta S is positive for the dissolution of urea. And student claims that the delta S contributes to the favorability. We already know that this is an endothermic process. Okay, that was mentioned earlier in this question. I'm not sure if I talked about that, but anyway, it is an endothermic process, but we're talking about delta S specifically here. So a positive delta S will lead to a negative delta G. So when delta S is positive, yes, this does contribute to the favorability of the dissolution. Now, the reason why there is no homework is that next week, Mr. Byrne and I will be teaching lessons focused primarily on AP practice. So that means that our practice will happen in the lesson. So no AP chemistry questions to practice because you'll be doing a lot of FRQ practice. So today's lesson was on Unit 9, entropy, free energy, and as it relates to thermodynamic favorability. I want to remind you to check out the helpful chemistry resources in the video description. Again, this has been Michael Faribaugh from Albemarle High School in Charlottesville, Virginia. Today is the deadline. If you have not contacted the College Board about your need for mobile tools or connectivity, let them know by filling out the survey at cb.org/tech. So next week, we'll do lots of FRQ practice in preparation for the AP chemistry exam. Thanks for watching and have a good weekend.